Hey everyone, welcome to the second video in the series on trig substitution for Math 1452 at Texas Tech University, which is Calculus 2. So in this video, we're going to start our examples on actually using trig substitution. In the last video, we talked about how trig substitution works and kind of where it comes from and how we can remember what we're doing with trig substitution. So we're just going to go straight off to the example section. So you may notice if you're filling in this on the blank worksheet that this first example takes up an entire page. So that will be common with these trig substitution questions just because they tend to be quite a few steps of rewriting the integral, using a substitution, integrating, and then putting everything back in terms of x. So first off, we're evaluating the integral 5 over x squared times the square root of 9 plus x squared. So when we see a square root of a number that's a square plus or minus x squared, we immediately are going to notice it. So this square root of 9 plus x squared is really the square root of 3 squared plus x squared. So remember that for these types of integrals, we're going to deal with the three trig functions, sine, tangent, and secant. And because the square root has a plus sign in it, that plus sign looks like a t, so we can remember that this is going to use tangent. So what we do here is we're going to use the substitution x equals 3, because that's the number being squared, times tangent of theta. And then we're going to use this to rewrite our integral. So I'm just going to go ahead and first, before I rewrite it, I'm going to kind of get some background of making this easier before we rewrite it. So I know that that's going to help me rewrite my x, but I'm also, because I'm using a substitution, I need to figure out how to rewrite my dx. So to do that, I'm going to take the derivative of x in terms of theta, and I get that the derivative of 3 tangent is going to be 3 secant squared theta, and then I'm going to solve for dx. So dx equals 3 secant squared theta d theta. So what this allows me to do is now I know how to rewrite my dx, and I know how to rewrite my x squared, because I just put in 3 tangent of theta, all of that squared. So let's go ahead and write all of that out too. So my x squared is going to be 9 tangent squared theta. And just to make it easier, I'm going to also go ahead and rewrite that square root. So I'm going to have that the square root of 9 plus x squared is the square root of 9 plus 9 tangent squared. And just like we did in the last video, I'm going to go ahead and simplify this square root by factoring out a 9. And then I know, using the Pythagorean identity, that 1 plus tangent squared is going to be secant squared. And then I can apply the square root to both of these terms. So this is going to be 3 secant theta. So I can go ahead and rewrite my square root and everything, so that way rewriting my integral is a little bit simpler. So let's go ahead and rewrite this integral using all of these substitutions. So we have the integral of, on my bottom, I'm going to have 9 tangent squared theta, and then I'm going to have times 3 secant theta, and then I'm going to have my 5 on top, and my dx is 3 secant squared theta d theta. So there's a lot going on in this rewriting of this integral. So first off, I'm going to notice that my secant, one on the bottom, is going to cancel with one on the top, and that my 3's are also going to cancel. And so I'm going to rewrite this as one fraction. So I'm going to have on top 5 secant theta, and on the bottom I'm going to have 9 tangent squared theta, and then a d theta on the back end. And so Oftentimes, to integrate fractions of trig functions, we're going to try and convert them to sine and cosine. So that's what I'm going to go ahead and do now, just because sine and cosine are a little bit easier to use substitution on, especially when we're dealing with fractions of trig functions. So if these trig functions weren't being divided, they were just being multiplied, we would use a strategy similar to that of integrating powers of trig functions. And there's a video series and worksheet on that strategy, but we're not going to do that here because these trig functions are being divided instead of multiplied. So in order to kind of combat that, we're going to change everything into sine and cosine. So first I'm going to pull my 5/9 in front of my integral. And then I have a secant, and that's times 1/tangent squared. And I have a secant times 1/tangent squared theta. And so I know that secant is 1/cosine. And that tangent is sine over cosine, but because it's in the denominator, I flip that and I get cosine over sine. And it's squared because my original tangent was squared. And I remember to write my d theta. I can see that a cosine on bottom is going to cancel with one of the cosines on top. So I have 5/9 integral of cosine theta over sine squared theta d theta. And now what this allows me to do is this allows me to use u substitution properly, where my u is going to be my sine of theta. So I'm going to write that again on this left-hand side. I'm kind of doing all of that work for my substitution. So my u here is going to be the sine of theta. My du d theta is going to be cosine of theta. And then when you do some algebra to solve for d theta, I get that du over cosine of theta equals d theta. And now I can rewrite my integral as 5/9 integral of cosine of theta over u squared times du over cosine of theta. And so just like normal, whenever we're doing a substitution, everything needs to cancel whenever we change our variable. So this is going to be 5/9 integral of 1/u squared du. And I can rewrite that as the integral of u to the -2 du. And then I can use the reverse power rule. So my 5/9 stays. I add 1 to my power and divide by that new power. And then I'm going to add a c. So this is 5/9 times u to the -1 over -1 plus c. So that's going to be -5/9u plus c. And then I put my u back as sine. So I have -5/9 sine of theta plus c. Okay, so I have evaluated my integral. However, for every time we use substitution, we want to leave the integral with the same variable it was given to us. So that means we have to go all the way back to x. So we went from x to theta and theta to u. Now we've gone back from u to theta, but now we need to go back from theta to x to leave the integral with the variable that we found it. So that means we need to solve for sine of theta. So to do that, we're going to draw that reference triangle like we talked about in the previous video. So I'm just going to draw it again over here on the left where I've been showing my work. So we have a right triangle. We have a theta here. I'm going to label, this is my side opposite theta, my hypotenuse, and my side adjacent to theta. And so I know based on my original first thing I wrote down for this question was the substitution, x equals 3 tangent of theta. So I'm going to use that here down below. that x equals 3 tangent of theta. I'm going to solve for tangent so that x over 3 equals tangent of theta. But remember that when we use SOHCAHTOA, tangent is opposite over adjacent. So this is opposite over adjacent. So that means that I really have a triangle where my opposite is x and my adjacent is 3. And then I can use the Pythagorean theorem, knowing that the sum of the squares of the sides equal let me say that one more time. We just know that a squared plus b squared equals c squared. So that means if we're solving for c, which is our hypotenuse, that it's the square root of a squared plus b squared. So this is going to be the square root of 9 plus x squared is the length of our hypotenuse. And so one indication that you're on the right track is that this was the original square root we started with, the square root of 9 plus x squared. So now we need to figure out the sign of this. And so again, using SOHCAHTOA, the sign is the opposite over hypotenuse. So that means that this is x over the square root of 9 plus x squared. So we just put that in. So this is negative 5 over 9 times x over the square root of 9 plus x squared plus c. But what I'm actually going to do is I'm going to multiply this by that reciprocal. So I'm going to multiply by x by the square root of 9 plus x squared over x, all over the square root of 9 plus x squared over x, because that's going to cancel out in my denominator. And then I'm going to be left with negative 5 square root of 9 plus x squared over 9x. And then I add c. So now that we have rewritten it in terms of x's, this is our final answer. So depending on how you are entering in these answers, if you're using an online homework platform, you did not need to simplify this. WebWork specifically is going to take this however you want it. If you're not using WebWork, it's harder for me at this present moment to say, but just check with your instructor on if you need to simplify it and get that square root out of the denominator if that's something they want you to do. So that's going to be it for our first example. You can see that yes, we did in fact take almost the entire page, but that's going to be it for this video. We will come back in the next video and do another example.